Alright guys, so we have a can here, contains some gas at a temperature 24 and a pressure of 360 kilopascals. We heat the can up to 50 degrees Celsius, and I want you to calculate the new pressure in the can. You're like, okay, well, I know that if we increase the temperature, pressure should go up, but I haven't learned a way to actually calculate the new pressure of the can. All I've done are conceptual problems so far. What am I missing? So there is an equation that we can use to calculate the new pressure, and it's derived from that ideal gas law. So we know from our formula sheet, we are always given the ideal gas law, PIV-NERT. So I'm going to show you how we can derive all these other equations from the ideal gas law. So anytime, like in a question like this, where we are given two temperatures and the problem has two pressures or two volumes, two of anything, we change one variable and we want to see what the effect is on another variable, we can use a modified version of this ideal gas law. Okay, so I have my ideal gas law, or what we commonly refer to as PIV-NERT, and I'm going to rearrange this so we can get an equation that we can use when our variables are changing. So let's assume that the moles of gas is remaining constant for a particular problem, like the same amount of gas is in the container. The only three variables that are really changing are the pressure, the volume, and the temperature. So let's ignore the N. We can ignore R because it's a constant. So I'm just crossing all those things that are remaining constant. And then let's just move everything to the same side of the equation. So I'm just going to move that T over to the left-hand side, divide both sides by T, and we are left with P times V over T. Okay, it's going to be equal to that constant value. Well, we know that that is going to have to hold true when we start to change the variables. So what we're going to do is we're going to put a 1, sub 1, next to each one of our variables. So that 1 equals the initial conditions of our gas. Okay, so I'll make myself a little note down here, or we'll just write initial. So those are our initial conditions. P1 times V1 over T1. And then what we're going to do is we're going to set that equal to the same exact variables, but this time we're going to write 2's. So that 2 means final, or the end. So what we have here, P1 times V1 over T1 equals P2 times V2 over T2. This is referred to as your combined gas law. So you'll see here we can use this gas law when our variables are changing. When we have two of each variable, we're going to use this combined gas law when we have two pressures, two volumes, and two temperatures. 1's being your initial state, 2's being your final state. Alright, so back to that original question. Go ahead and pause, record the question, get all the information down, and then come back and I'll show you how to solve. Okay, so what we're examining here in this problem is a relationship between pressure and temperature. And we know, heat them up, speed them up. So the higher the temperature, the faster the particles are moving, the more they're going to collide with the container, and they're going to collide with more force. So that's why temperature is going to increase the pressure of our gas. And you're wondering, okay, well, how do I go about calculating this? Well, let's isolate some variables here. We know that the starting temperature is 24, that's our T1. We know the starting pressure is 360, that's your P1. We change the temperature to 50 degrees Celsius, that's your T2. And they want to know what is the new pressure. So they want us to solve for P2. What's being held constant here is the size of the container. It is a rigid container. Vocab word. Rigid means constant volume. The can is not changing shape, so it's holding and retaining its same volume. So, how do we solve this? Well, we take our combined gas law, which I've written out over here. P1 V1 over T1 is equal to P2 V2 over T2. And since the volume is being held constant, I can cross it out. And so I'm left with this equation, P1 over T1 is equal to P2 over T2. And this shows how pressure and temperature are directly proportional. As temperature increases, as you see here on the graph, as temperature increases, pressure also increases. So now we're going to calculate for this question. So we're going to use this equation, P1 over T1 equals P2 over T2, and it becomes a plug and chug. Some things to note, though, about units. Temperature, guys, always has to be in Kelvin. Every single time. Pressures, though, as long as both pressures are the same unit, it could be atm for pressure, it could be torr, it could be kilopascals. So as long as P1 and P2 have the same unit, you're good. But temperature, they have to be Kelvin every single time. So we got to convert. All right, so let's plug and chug into our equation here. P1 is 360 kPa over T1, 297 Kelvin, is equal to P2, which we don't know, over 323 Kelvin. Solve for P2. So P2 equals 391.5 kilopascals. And I know it's going to be kPa because I know the unit of P1 and P2 should be the same. So since my P1 was in kPa, my P2 is also going to be in kPa. Now, sig figs. We are going to have 2 sig figs. Oh, I'm going to cheat here. Put a dot after the 50 degrees Celsius. Make that 2 sig figs. So we're going to round this to 2 sig figs. 390 kilopascals. One good habit to get into practice of is to double check your answer to see if it is reasonable. We increased temperature, so we would expect the pressure to also increase. Did my pressure increase? And yes, it did. Our P2 is higher than our original P1, so this answer seems reasonable. If I got an answer that was lower than the original pressure, then I would need to go back and double check my math and make sure I didn't do anything wrong with my algebra, or maybe I just plugged things wrong into the calculator. So it's always a good idea to get into a mental double check. Is my answer reasonable? I expected P2 to be higher. It is here, so I'm thinking my answer is reasonable. All right, next example problem. Press pause, come back, and we'll work it out. All right, now that you've had time to record the question, let's see what's going on here. We've got gas. It's at a certain temperature, 15 degrees Celsius, and a certain pressure, and a certain volume. Ooh, it's got a lot of things. What volume will this gas occupy at 38 degrees Celsius and 1 atm? Okay, well, I noticed that 1 atm, hey, that's the same. I can ignore that. That's constant pressure, so that's not going to affect anything. But we do note that we have a starting temperature and a starting volume, and they want a new volume. They want us to calculate V2, and they gave us the new temperature. So this looks like problems with 1s and 2s. So I need that combined gas law again. Alright, so I take that combined gas law, P1V1 over T1 is equal to P2V2 over T2. This time, the pressure is constant. So I cross out the P's and I am left with this equation, V1 over T1 equals V2 over T2, which is essentially saying that volume and temperature are directly proportional. As temperature increases, volume is going to increase. So again, heat them up, speed them up. As those particles move faster, guys, they actually lose attraction for one another at a higher temperature. And so as the IMFs decrease as temperature increases, the particles are able to get farther and farther and farther and farther and farther apart from each other. And so the volume gets bigger and the container expands. This is all assuming, of course, that pressure is being held constant. So let's solve. Let's plug everything into our equation and solve for V2. Okay, here's my substitution into the equation, and now we're going to solve for V2. V2 equals 2.79 liters. Again, looking at your units in your problem, V1 and V2 have to have the same units. Temperature has to be in Kelvin. We always convert to Kelvin. And now let's check how reasonable our answer is. The temperature increased, so I expect the volume to also increase. And so I need to make sure that my calculated V2 answer is higher than the original V1, which it is. So my answer of 2.79 liters is reasonable. Okay, question number 5. Again, hit pause, record the question, and we'll come back and solve. All right, so we have a 1.53 liter sample of a gas, V1. It is initially at a pressure of 5.6 times 10 to the third pascals. So that's our P1. The pressure is changed to 1.5 times 10 to the fourth power pascals. That's your P2. They're telling me constant temperature, so I can ignore temperature. What will be the new volume of the gas? So they want me to solve for V2. So I got some 1s and I got some 2s. I need that combined gas law again. Here's our combined gas law. P1V1 over T1 is equal to P2V2 over T2. Since temperature is being held constant, I cross it out and I am left with this equation, P1V1 equals P2V2. And you'll notice here that this graph shows that inverse relationship between pressure and volume. So let's go ahead and substitute in our variables into our equation and solve for V2. Okay, here's my substitution into the equation. Now let's solve for V2. I get a V2 of 0.57 liters. And again, a word about units plugging into this equation. As long as P1 and P2 are both the same unit, in this case pascals, we're good. As long as V1 and V2 are both the same unit, in this case they're both going to be liters, I will make V2 liters. So my units work out, and let's check how reasonable my answer is. What happened to the pressure? Well, the pressure started off as 5.6 times 10 to the third pascals. It increased to 1.5 times 10 to the fourth pascals. So just watch out for your scientific notation. Our original is 10 to the third. Our final is 10 to the fourth. So pressure increased. It got bigger. So what should happen to the volume? The volume should decrease, which it did here, decrease to 0.57 liters.